Hello, my name is Chris Mack, and welcome to our second part of our three-part series on the introduction to mask making. Last time we gave an introduction to what a photomask was, how it's used in the lithography process for semiconductor manufacturing, and also gave a brief outline of the steps involved in mask making. In this lecture, we'll focus on one of those steps in some detail. I mean, not a terrible amount of detail, it's a complicated subject, but we're going to talk about mask writing with e-beams. Now, we can write masks with lasers as well, but those are for lower resolution applications. All of our high-end masks today are written using electron beam lithography. Now, the key to the lithography process used in making masks is that we don't have a mask to start with, right? We have to use direct write lithography. And e-beam lithography is the direct write lithography of choice for high-end mask making today because of the resolution. Now, there are many different kinds of e-beam mask writers with different properties. So the things to keep in mind when thinking about the differences, first, the number of beams, whether it's a single beam, like most of them are today, or a multi-beam writer, like we're working on for the future, but also the electron energy, the shape of the beam, whether it's a Gaussian shaped beam, a spot, or a shape that can be made into a rectangle or a triangle, and then the writing strategy. All of these things affect throughput and resolution, and in particular the resolution throughput trade-off. Built into resolution are things like pattern fidelity, critical dimension control, and also registration or overlay control. The different kinds of e-beam tools all have the same basic components. They have an electron gun, or a source that supplies the electrons. They have some optical system that moves the electrons around. We call this an electron column. It shapes the electron beam, it focuses it. It includes a beam blanker for turning the beam on and off, and it sends those electrons to the resist-coated substrate, the photomask that we're going to write. There's a mechanical stage that positions the mask under the electron beam and a handling system to move those masks in and out, and finally a computer control system. And this is, of course, every tool has some kind of a computer control system, but here it's critical because we have to put in a huge amount of data to tell the blanker and the stage where to move and where to turn the beams on and off in order to create the patterns we're trying to write. So the data path, the ability to very quickly move a lot of data from the data source, the file, into the writer is a very critical component of an electron beam lithography tool. Let's look at the gun, the source. There's two basic ways, there's actually lots more ways, but the two basic common ways in which we can generate electrons is thermally or with an electric field. A thermal source essentially takes a piece of metal, heats it up very, very high in a vacuum, and boils off the electrons. We have enough thermal energy to overcome the work function of the barrier that would normally keep the electrons within the metal. The simplest kind of source would be this tungsten filament here, which we send a lot of current through to get it very hot and electrons come off the tip. Lab 6 is the most popular source for high current densities for thermionic sources. And again, these are done in vacuum. A field emitter gun takes some kind of a source, a tip, tungsten for example, but could be carbon nanotubes, and creates a very, very sharp tip and applies an electric field to pull the electrons off that surface. They tend not to be as high a current as the thermionic sources. Once we have a source of electrons, we need to move them where we want them to go, and we can deflect the beam and focus the beam using electrostatic and electromagnetic kinds of sources. Electrostatic source is simply, or excuse me, not source, but deflector. Electrostatic deflector is simply a pair of parallel plates that I apply a voltage to. The negatively charged electrons like the positive voltage and they'll get bent towards that positive voltage. For the case of a electromagnetic bending or deflection, we run a current through a coil and create a magnetic field. A moving electron passing through a magnetic field will experience a Lorentz force that will also bend the electrons. So in the middle we have the equation for that force. With these kinds of electrostatic and electromagnetic forces, we can vary those fields and forces as a function of radial position and create a lens. In fact, we talk about E-beam columns as being optical columns, or like optical columns. They're made of lenses. The lenses have aberrations and behaviors that are very analogous to the way light goes through glass or optical lenses. And unfortunately, these lenses also have aberrations. Spherical aberration, chromatic aberration, different velocities of electrons will experience different forces and will be bent differently, just like different wavelengths will experience different refractive index in an optical lens. So we need to correct for these aberrations, but that's very difficult to do. As a result, we tend to be aberration limited in our lenses in terms of their quality, and we are limited to fairly low numerical apertures. But that's okay because the wavelength, the de Broglie wavelength of an electron is also very, very low. So even though the numerical aperture is low, we still get a very high resolution. Here's a couple of pictures from the literature on showing you both a schematic and a cross-section of an actual tool, how these lenses are used in deflection plates and beam blankers, etc., from the source down to the writing surface. The next thing we need to think about is how we're going to write. What is our writing strategy? And the strategy does depend on the beam shape. For example, we might have a spot. If we have a spot of electrons hitting the substrate, the easiest way to write a pattern is with a raster scan. We simply scan the beam back and forth and have a beam blanker that turns the beam on and off where we want it to write and where we don't want it to write. This is a fairly easy technique. It's the way the old CRTs, cathode ray tubes of our old television sets used to work before we all got flat screen TVs. And it's very easy to manage the data and to build a system to do this. However, it's also slow. We can adjust the spot size to make it faster, but that gives a very direct trade-off between resolution and throughput. Higher spot size allows us to write faster, but with lower resolution. We can do a vector scan. This is like a raster scan, but we only are scanning the beam back and forth within the regions that we want to be exposed. This can be a lot faster for the case of sparse patterns where we only have a little bit of the area of the mass that we actually want to write with our electrons. But by far the most popular way of doing things today is a variable shape beam where we project an entire shape onto the wafer at one time. The shapes are typically rectangles and sometimes triangles as well. Well, I'm fond of saying that the best way to picture it is with a picture, so let's look at these three writing strategies pictorially. If I have a Gaussian beam, that is a round spot of electrons, I can raster scan or vector scan those. So in a raster scan, I'm scanning the beam across, and it's turned off until I reach the spot where the data says I want to write, and then it turns it back on. And then I continue the scan, but now I'm actually writing. I come down and I scan in the other direction. The software, the data itself is turning the beam on and off in the right place. And I simply scan back and forth. In a vector scan mode, I'm doing the scanning back and forth, but only within the regions that I'm trying to expose. But I can do much, much better with a shape beam system in terms of throughput and resolution, or the throughput resolution trade-off. With a shape beam system, I'm projecting one rectangle, which we call a shot, at one time. So I have an entire rectangle worth of electrons all projected down and exposing one stop. I step the substrate to a new location. I adjust the size of the rectangle and I expose the next shot. And I keep doing that. Sometimes I can even have triangles depending on the system. Usually a very limited set of triangles like right triangles. But I can then write up the pattern in this way. As you might imagine, this requires, as we talked about in the last lecture, a fracturing step ahead of time where the data, which is made up of these polygons, is fractured into individual shots, and then the shots are fed to the beam writer. Commercially, we've been using e-beam lithography as the dominant way of making masks since at least the 80s. The most popular tool was the MEBIS tool from E-Tech. E-Tech was later bought by Applied Materials, or AMAT. This was a raster scan system that used 10 keV and was very, very popular for a long time. But then, when we got down to about the 130 nanometer node, the Gaussian beam raster scan had just too ugly a trade-off between resolution and speed. And since about that time, all of the high-end masks have been made with 50 keV variable shape beam tools. And for that reason, Applied Materials, in fact, discontinued the MEBIS line of mask writers, I think in 2005. So we've been writing for a long time now with the 50 keV variable shape beam tools from companies like JEOL, Vistec, which used to be Leica, and NuFlare out of Japan. These tools have been working very well, but we're starting to approach the limits of this resolution throughput trade-off for these tools, and below 10 nanometers we might need a new approach, multi-beam writing. We'll talk about that at the very end of this lecture. Another important parameter is the electron energy. Right? I said the MEBIS tool had 10 keV electrons, and these variable shape beam tools have 50 keV. What's the difference? What's the trade-off? Well, there's a resolution impact, a throughput impact. If we think about higher versus lower beam energy, what does a higher beam energy mean? What does 50 keV mean compared to 10 keV? Well, the first basic thing is the scattering within the material. When electrons go into a material, it scatters, and it has both a forward scatter and a back scatter distance. So if I show you what the electron energy looks like inside of the photoresist, it's going to look something like this. I have a spot of electrons hitting the photoresist incident at this point. It spreads out in a forward scatter array, and most of the energy is contained in the forward scatter spread, but there's also a longer backscatter spread. And both of these things have an impact on resolution. If I go to higher beam energy, I have less forward scattering, therefore a smaller spot size in the forward scatter sense inside the photoresist. That results in better resolution, better CD control. I can use it with a thicker resist because it doesn't spread out as much, and so it maintains its shape through thicker resists. But that higher beam energy has more backscattering. Now the backscattering impacts proximity effects, how one feature affects its nearest neighbors. And we have to correct for these proximity effects, and that becomes more difficult at the higher beam energies. But in general, higher beam energy is going to give you better resolution. However, it also gives you lower resist sensitivity. This is simply because more electrons will pass through the resist without interacting with the resist. And therefore the resist is less efficient at capturing those electrons and the electron energy in order to cause chemical change in the resist. If you have lower resist sensitivity, then it takes longer to expose the resist, and the system becomes slower. Also, you get more electrons making it all the way to the substrate, heating up the substrate, and possibly causing damage in the substrate. This is also something we have to take into consideration and try to mitigate the difficulties. Most of the mask writers use energies between 10 keV and 100 keV, but as I said, 50 keV is probably about optimum today. So I've mentioned this throughput versus resolution trade-off. Let's look at what limits resolution, then we'll look at what limits throughput, and we'll see that some of these variables are the same variable in opposition to each other. There are three things that could possibly limit resolution depending on what we do. First is the spot size due to the electron wavelength in the lens NA, and aberrations in the lens. That is, what is the theoretical best I could do with any given electron column? There's also electron interactions, Coulombic interactions. If I have two electrons and I try to put them right next to each other, well, they repel each other. They both have an electric charge that's negative, and Coulomb's force will push them apart. So if I have too high of a current and I try to squeeze too many electrons down into a small space, they will spread out. But for most systems, the limit to resolution is the electron scattering in the resist and in the substrate that causes this forward scattering and back scattering as well. Sometimes, though, it's some combination of all three of these things that is impacting resolution. Throughput, on the other hand, is a function of the size of the spot, if we have a Gaussian system, the size of the address grid, that is how finely we can move the stage and change the size or the shapes of the rectangles in our shape beam system. Also, we can get higher throughput if we use a higher current. Well, you can already see some of the trade-offs here. A larger spot size is going to cause a lower resolution, even though it causes a higher throughput. A higher current can result in electron-electron repulsion, which can lower your resolution. We can also get higher throughput by having a faster stage, but then faster stages sometimes are harder to control. So you see that there's a number of ways in which we have a trade-off between resolution and throughput. In general, higher throughput results in lower resolution, and higher resolution results in lower throughput. In fact, this trend has been noticed for quite some time, and Don Tennant described about 20 years ago this trade-off in what has now become known as Tennant's law. He looked at a large number of lithography tools, from optical step and repeat reduction printing that we use in semiconductor manufacturing and wafers, through scanning tunneling microscopes, manipulating atoms one at a time, and everything in between, with e-beam lithography as one of these multiple of these systems of various types. And he found that the resolution versus the areal throughput, that is the square area of substrate that I can expose in a given amount of time, follows a particular trend. On this log-log scale, it looks like a straight line, but in fact, if we look in detail, we find that the areal throughput goes as about the resolution to the 5th power. Now, what does that mean, and why is that true? Resolution, or the areal throughput, is resolution to the 5th power. That means if I build a tool with higher resolution so that R becomes a smaller number, throughput goes down. How much? Well, according to Tennant's law, if I can cut the resolution in half, go from 10 nanometer, say 20 nanometer resolution down to 10 nanometer resolution, that factor of 2 improvement in resolution results in a factor of 32 reduction in throughput. That is some ugly scaling. Nobody likes that kind of scaling. And this is the big challenge for e-beam lithography. Where does this power of 5 come from? Why is it so bad? Well, first of all, we have the pixel size itself. Right? If the pixel size is R squared, if I reduce the resolution by a factor of 2, the R by a factor of 2, I have to have 4 times as many pixels. If you have a constant pixel throughput, then your areal throughput will go down by a factor of 4. But what about the rest of the powers? We still have an R cubed left. Well, shot noise is another factor. You can push the sensitivity of a resist, the resolution per unit dose, only so far when you start suffering from shot noise. In other words, there's a minimum number of electrons per pixel required in order to control that pixel properly. If you get too few electrons in any given pixel, you start losing control due to the statistical noise called shot noise. If there's a minimum number of electrons per pixel, then I'm going to have to write longer as I shrink the size of that pixel if I have a constant current density. That gives us now an r to the 4th power, and the r to the 5th is probably just an added set of kind of normal control-related things. It's harder to control small pixels well, so you have to do things a little bit more slowly to make it happen. This is an empirical law. It's not a law of physics, but probably the r to the 4th power is going to be very hard to overcome. And this has had its impacts on mask writing. Up until about 2010, we could write a high-end mask in about 6 hours. Right? Every time we increased the number of pixels by making the resolution smaller, we have more pixels we have to write, or if we have the case of shots, we have more shots we have to write. We've been able to increase the writer pixel throughput accordingly so that we kept the time it took to write a high-end mask at about 6 hours. Well, we haven't been able to do that lately. Since about 2011, write times have increased by about 25% a year, every year. This is because of the fact that we can't increase the current density forever. We're hitting limits on current density. OPC complexity, optical proximity correction complexity, is making the masks much more complicated with a larger number of shots. Today, masks typically take 15 to 20 hours to write instead of 6. And in fact, I've even heard of masks that require 70 hours. That's 3 days to write a mask. This is a problem. It's a problem for cost. Right? The longer it takes to write, the more costly it is. But we also have to worry about the stability of the tool. Can the tool stay stable as it's writing over such a long period of time? If a tool can write for 1 week before it fails on average, well, how many times will it have a problem with a 70-hour write time? This is a big deal. And as a result, we're looking at breaking out of the paradigm of a single beam for our mask writing. Many companies have multi-beam tools under development today. Slow serial writing can be sped up if we write multiple features in parallel instead. There's 2 basic ways to do that. We can have multiple miniature e-beam columns. We can try to make these e-beam columns using MEMS-like technology. But what is probably the most effective way is to have one column but have multiple pixels, each of which can be controlled individually. This is the technique that most people are pursuing, and here I show a picture of one example. I have a plate. The plate has some holes that are in that plate. I illuminate this plate with a flood of electrons. Inside each hole I have beam blankers, so MEMS-like technology that can turn on and off the individual beams. I have some individual beam deflectors that can move the beams around, and then a system that can focus them down to individual spots. So, for example, I might have 512 by 512 individually addressable beamlets. I then can do a reduction with the optical system of my column to reduce things, say, 200 times. And now I've got 512 by 512 individual pixels all writing in parallel. And that can make things faster. These tools are not yet commercially available, but I think we're going to see them on the market within the next few years. And this might solve our problem with write times as we hit the 10 nanometer node and below. So what are the mask writing big ideas? All high-end masks today are written with 50 kV variable shape writers. We do have laser writers for our lower resolution applications, but E-beam is the technique for high-end masks today. Mask writing speed goes down as the resolution of the writer improves. This is called Tennant's law. It's an ugly trade-off, and as a result, high-end masks today are taking too long to write. It's becoming a big problem. That's why we are moving towards multiple beam E-beam writers, and I think in the near future we're going to see some of these in use in mask making. Well, that's the end of the second lecture in this three-part series on mask making. Next time I'll talk about mask inspection, repair, a little bit of metrology, and also talk about some of the unique challenges of EUV masks. Thank you.